So what is weighted in the GATE exam is something like 8 to 10 marks here. So this is completely maths. So this is completely maths. This is more mathematics. Let's say 95% mathematics plus 5% concepts. This is how the system is. 95% maths and 5%. Okay. So what are the various topics which are involved here is, so first Laplace transforms and first order systems. Second order systems. Closed loop control and stability. Frequency response. Advanced control systems. So these are the multiple topics in PDC. Laplace transforms and first order systems, second order systems, closed loop control and stability, and frequency response. So this is extremely important topic in the entire system. So this is the big topic and important topic. The main subject lies in this particular chapter only. So overall every year you will get a minimum 2 marks question from here. Minimum 2 marks question. And rest 20 classes for completing the subject. So every day, let's say 1.5 hours. Overall, I'm expecting, let's say, something like 30 hours class minimum. So maybe 20 classes. So for 1.5 hours, it will be 30 hours class. So that is the expectation. So overall, what I want to say is this is purely math subject. This is purely mathematics subjects. So instrumentation will be covered at the end. So once it is entirely completed, then at the end I'll complete, let's say, one class for the instrumentation. Clear? So this is how the entire outlay of the program. Any doubts? There are two books for this one. One is Kaufner and Stephanopoulos. So Kaufner will be simple and easy. Stephanopoulos is like CRE, Levenspiel and Fogler. So like this, you can follow anything. Kaufner and Stephanopoulos. These two are the books. Clear? So we'll go to next class. So this one, what is objective of PDC? So if you try to see, this subject is called as process dynamics and control. If you see the spell of this subject, process dynamics and control. Why this there? Because two topics, process dynamics and process control. These are two topics, dynamics control. Okay, so is there any problem in my voice? So I'll just move to another room. Bye. So can you hear my voice now? Fine. Okay. I'll just move to another room. So if you see, this topic is two topics, basically process dynamics and control. So process dynamics is one topic and control is one topic. Let's say what you are trying to do in this particular subject. So let us take a simple example of CSTR. You have feed A going in, and then let's say B is the product going out. Now this is an exothermic reaction. So you need to take out the heat. So you have a jacket something like this. In this one, cooling water is going in. Clear? Now what is your objective here is maintain the CSTR temperature at the rate of 60 degrees centigrade. This is the objective. Because the reaction is something like this. Why you want to maintain 60? A gives B, maybe A gives, let's say C, A gives D. So B will be possible at 60 degrees, maybe C will be at 50 degrees, and D will be at 70 degrees. This is how the reaction is. Now, so my objective is I want to get B, so this is my objective. So that is why you want to maintain the CSTR at 60 degrees centigrade. Clear? So accordingly, you need to calculate the cooling water flow rate. So accordingly, so this is the reaction mixture. So accordingly, you have to calculate the cooling water flow rates. So let's say you have a reaction. This A gives B and releasing 100 joules per mole. 100 joules per mole is, let's say, minus 100 joules per mole is, let's say, heat of reaction. Suppose now, let's take two scenarios. So you have A gives B 100 joules per mole is the heat of reaction. So if you don't remove any heat, don't remove any heat, then we have done in CRE heat balances. You write the heat balance, that is enthalpy in equal to enthalpy out plus enthalpy of the reaction. Then what is the temperature of CSTR is you are reaching is 100 degrees centigrade. So just for example, I am saying all these numbers roughly. If I do not remove any heat, your temperature of the CSTR is 100 degrees centigrade. So because let's assume that here the feed is coming at 40 degrees centigrade. Your feed is coming at 40 degrees centigrade. So if you don't remove any heat, So your entire temperature of the CSTR will go to 100 degrees centigrade. How do you get that 100 degrees centigrade? From the energy balance. Now, if I remove, let's say, so remove 40 joules of heat. Let's say 40% of the heat, or let's say 40% of the heat. Then the temperature of the CSTR is, let's say, 60 degrees centigrade. 60 degrees centigrade. Suppose if you remove 100% completely, then what is the temperature of CSTR, which is equal to feed temperature, which is 40 degrees centigrade. So basically, if I don't remove any heat, your temperature of the CSTR is 100 degrees. If you remove 40% of the heat, then your temperature of the CSTR is 60 degrees, basically 40 joules. And then if you remove 100%, your temperature of the CSTR is 40 degrees. So this is my temperature of the CSTR. This is how I want to operate. Now for 40 joules of heat, how much cooling water is required? So 40 joules of heat I want to remove. Let's say 40 joules per hour I want to remove. Then what do you do for cooling water? MCP into delta T. So let's say what is my cooling water inlet temperature is 35 degrees centigrade. Outlet is 45 degrees centigrade. So how much heat I have to remove is delta T is 10. CP, let's say M I have calculated, let's say 1 ton per hour, roughly. So all these numbers I am saying just to understand the problem. So basically, now if you go back to your CSTR and analyze, if you send 1 ton per hour of cooling water flow rate, then it removes 40% of the heat. Then your temperature of the CSTR is maintained at 60 degrees centigrade. So your objective here is maintain the temperature of the CSTR at 60 degrees. Like this, for every unit operation in the problem, there is one objective. So why PDC has come into picture is, like if you want to maintain the variables in a plant at a particular concentration or at a particular temperature. Let's say I want to operate my temperature of the reactor at 400 degrees. Let's say I want to operate my distillation column to get a purity of 99%. So if I want to operate a distillation column at a temperature of 500 degrees centigrade, I want to operate my distillation column at minus 100 degrees centigrade. Like this, so every unit operation in a plant has some objective to maintain. Otherwise, actually will not meet the purity of the product. Let's say you are operating a diesel hydrotreater, you want to operate the distillation entire reactor at 400 degrees centigrade. Clear? So every objective, so that is where the PDC comes into picture. PDC's main objective is maintain the variables at a particular temperatures or at a particular objectives. So how 40 degrees has come? Suppose if you remove the entire heat, whatever the inlet temperature will be equal to outlet temperature, no? So have you understood till now? Just spend some time on the initial part. Now, having understood this particular problem, now let's go to another point. So that is, if you want to maintain temperature of CSTR at 60 degrees centigrade, if you want to maintain temperature of CSTR at 60 degrees centigrade, send 1 ton per hour of cooling water flow rate. Cooling water flow rate. Now everything is fine. Now you have started operating the plant. So now the temperature of the CSTR is extremely good, 60 degrees, because you are sending the 1 ton per hour of the cooling water flow rate. Now a situation has come. Now you have not constructed still the plant. You are analyzing this entire things on a paper or on a system. So what is, somebody asked a question, what happens if suddenly the inlet feed temperature rises to 50 degrees centigrade? What happens? Suppose, let's say somebody asked quietly one question. So if the feed is 40 degrees centigrade, you are sending 1 ton per hour of cooling water flow rate. So you are maintaining the temperature at 60 degrees. So as long as my inlet temperature is 40 degrees, I don't have any problem. So what happens if the inlet, why this inlet temperature is changing? Because there is a heat exchanger in the upfront. That heat exchanger is not working fine. So maybe some foul it has happened, or something happened to that heat exchanger, so it could not able to heat up to or cool up to, or let's say it is sending a flow rate at 50 degrees centigrade. Then what happens? So your temperature of feed is 40 degrees centigrade. Suddenly the temperature has become 50 degrees centigrade. Then what happens to the outlet temperature? Will it be same? Will it be same? 60 degrees. So slowly it will rise and then it settles at some new value, maybe 70 degrees centigrade. Maybe 70 degrees centigrade. Then what happens? Instead of B, you will get D. Clear? Instead of B, you will get D. So this 50 degrees is what you call it as, this is what you call it as a disturbance to you. This is what you call it as disturbance. So disturbance. Then what do you do? What you have to do now? When you see it has become 70 degrees, when you see it has become 70 degrees, so you have to increase the cooling water flow rate. Now you have to increase the cooling water flow rate because you have to take out more heat out of the system. Then what you will do is, suppose if you are operating the CSTR, you go and open the cooling water valve. Go and open the cooling water valve. Agreed. Then somebody asks a question. So like suppose if you are doing like this, how many persons you have needed in a plant? Suppose if you are operating, let's say, refinery. So for every operator you need, for every parameter you need one operator. Clear? So that operator has to look at the system variable, and then if there is a change, then he has to do something to bring back the variable back to 60 degrees centigrade. Suppose if you are operating the CSTR, then you should go and open the cooling water flow rates. So that is how you control the variables. Now the next question is, can we have an automatic system? Can we have an automatic system which maintain the temperature of CSTR at 60 degrees centigrade irrespective of disturbances? This is, otherwise how many people you need to operate the plant will be, maybe 100 or 200 people has to be in the plant. Clear? So how do you do? Then that is, That is what is called as automatic system. So which will take care of maintaining the variable. Now, when you are talking about an automatic system, there are two ways. One is two ways of operating. One is look at temperature of CSTR. If it increases above 60 and if it is increases above 60, open cooling water. If it decreases below 60, close cooling water flow rate. So this is one way of task. So you are talking about, let's say, an automatic system. That is, here what you are doing is, why the temperature is going above 60 and below 60, because somebody has affected, no, there is some disturbance which has affected my system. That is why my temperature has automated, or let's say, fluctuating about the 60 degrees. Sometimes it is going beyond 60 degrees, sometimes it is going below 60 degrees. So there is some disturbance. Clearer. Now in this system, I am not bothered about my disturbance. What I am doing is, let the disturbance affect my system. Let the disturbance affect my system. Then I will take the control action. So this is what you call it as feedback control. Another thing is, so you are trying to design an automatic system. So what is another way of doing is, so now look at temperature of feed. Now here what you are doing is, this is an advanced system. So what you are doing is, you are monitoring the disturbance itself. Look at the temperature of the feed. If it increases above 40 degrees, then open cooling water flow rate. If it decreases below 40 degrees, then close cooling water flow rate. So this is another way of operating the system. Let's say this is what is called it as feed forward control. This is another way of system, which is feed forward control. So I'm trying to explain all the 5 chapters in one example. So it may be sometimes difficult to understand everything, but these topics will be again repeated in the when I am discussing the everything. Feed forward means, if you are monitoring the distance, see, let's assume that suppose if you get a cold, automatically you will get a fever, correct or not? So if I have cold, then finally we'll get a fever. When you have cold itself, taking fever tablet is feed forward control. Knowing that cold will cause fever, and take advanced, let's say, medicine which is, let's say, paracetamol, taking based on cold, is what is called as feed forward control. Feedback control is, you do not take any action when you have a cold, but when you start seeing fever in you, then taking the paracetamol is something like feedback control. So feedback control, what you are doing is, let the disturbance affect my parameter, then you are taking the control action, is what is called as feedback control. Feed forward control is, you monitor the disturbance itself and take the control action. In the second case, what happens is, you are not letting the disturbance affect your parameter, correct or not? So there is no better, which one is better or good or bad. So mostly in the entire plant, you will have a feedback control. I'll tell you why feedback control gives, let's say, more flexibility later, but there are two ways of control strategies. Temperature of feed, anything which is deviating from 40 degrees is a disturbance to me. Now, how do we design a feedback control? How to design a feedback control? What are the elements that you have in a feedback control? So now you have a CSTR. So you have the feed coming in, product going out. So clear. So this is what is, let's say, A, B, cooling water. So what do you have is, the first thing is you should measure this temperature. So you have a measurement. So you should have a measurement. Then measurement will be sent to this is sent to the controller. So you will come to know all these things in clear, let's say in chapter 3. But I am trying to give a heads up in the upfront itself. You have a controller to whom you will tell that maintain at 60 degrees. So you will give a set point. That means set point means 60 degrees. Accordingly, it opens the control valve. So now this is handed over to a automatic person. So you have a measurement. Let's say if the measurement comes 60 degrees, it compares it with set point, then accordingly it doesn't do anything on the control valve. Let's say if my plant temperature, let's say this is sitting in the plant, this is what is the control room. You have in the control room. So this is the field. From the field you have measured signal. This measured signal is coming to the controller. The controller will compare with its set point. Accordingly, it opens the cooling water flows. This is what is called as a feedback control design, or let's say feedback control. So basically, this is the objective of the entire, let's say, feed control strategy. Suppose if you want to convert this to feed forward, what do you do is, instead of measuring the temperature of CSTR, you do measure the temperature of the feed. Suppose if you put, let's say, something like the measurement to here, then what happens? This become a feed forward. So we will discuss later on, maybe all these things in detail, but I'm trying to discuss the entire things at one go. Suppose if the temperature comes below 60, then you close. See, basically what the fundamental mechanism is, if you open more cooling water, then it takes more heat, then the temperature drops. If you send less cooling water, then the temperature rises. That is the fundamental mechanism. Suppose let's say my field temperature is 50 degrees. Then what do? You should close the cooling water flow rate. Maybe you are sending more cooling water than required. That is the fundamental principle. That means you should have, let's say you take a distillation column. Your objective is to maintain the purity at 99%. Suppose if you want, if you currently my distillation column has a purity of 97, what do you do with the recycle flow rate? Do you increase the recycle flow rate or decrease the recycle flow rate? To improve the purity of a distillation column, will you increase the recycle ratio or decrease the recycle ratio? Increase, no? That is what here also same. So now to decrease the temperature, now principle simple is, if the temperature is going beyond 60 degrees centigrade, then you will have to increase the cooling water flow rate. If the temperature is going below 60 degrees, you have to close the cooling water flow rate. This is the fundamental mechanism. So guys, I want to tell one thing. Suppose if you do not understand what I'm saying till now also, don't get, let's say, upset, because I'm trying to explain all the 5 chapters in a simple example, so that at least you will have a curiosity what am I going to learn in this particular subject. So I just wanted to put question mark, or let's say answer to your curiosity. Let's say what I'm might trying to learn in this particular subject is my overall objective. So that is why I try to explain, maybe I'll try to explain the entire things. So what is the objective of the PDC? Objective of the PDC is, so basically what happens if I don't study PDC is you have to put a person in front of every unit operation. Suppose I have, let's say, 15 unit operations in the plant. That means I need 15 people to operate the entire plants. One more thing is the let's say temperature of the CSTR is going beyond 60. So let's assume that I don't study PDC and I'm comfortable with operating the manpower. So my temperature of the CSTR is 60 degrees. Suddenly it is started rising 60, 70, 80, 90, and then maybe design temperature of the vessel, maybe let's say 75. See, by the time let's say I'm watching the, let's say, the temperature of the CSTR. So now I have realized that the temperature of the CSTR is 70 degrees. By the time I get up from my seat and go and open the control valve of cooling water flow rate, the reactor may explode because the temperature of the CSTR is continuously rising. Why the temperature of the CSTR is rising? Because there may be some disturbance which is affecting my temperature of the CSTR. So that is why because signals are faster. So whereas we can't move with the signals, no, let's say the signals in the plant are 4 to 20 milliampere signals, they will go at a faster speed that you can't do it in a, let's say, using the manpower. So that is why what is the objective of PDC is simple. Let's say I am operating a polypropylene, let's say ethylene plant, propylene plant. So now to make polyethylene, I need ethylene of purity 99.9%. Suppose if I don't have PDC, suppose sometimes my distillation column gives 99 purity, sometimes my distillation column gives 97, sometimes my distillation column gives 95 also. What happens with the PDC is it will maintain the variables at a particular value so that you can have a better market for the product or you can have a better operating parameters. Let's say if I don't have a control over a hydrocracking temperature, how many scenarios have you seen, like a plant exploded, or let's say reactor exploded, or let's say HPCL plant, let's say. So all these scenarios will come because there is no proper control of the entire system. Clear? So the safety system, this is basically maintaining the variables at a particular temperature, and it affects the safety of the temperatures also, or let's say safety of the plant. So the first that I have discussed is what is the objective of the PDC is, and first thing is consider this as a two topics. Don't read it as a process dynamics and control. Clear? So don't read it as process dynamics control. Process dynamics and control, because process dynamics is different, control is different. Because so what is PDC objective is maintain the variable at a particular temperature. So I'm explaining a CSTR. Simple, it is an exothermic reaction. And so you have studied, let's say, this is, if I remove the entire heat, then the temperature of the CSTR is 100 degrees. If I remove only 40 joules of heat, the temperature is 60 degrees. If I remove the 100 degrees or complete heat, the temperature of the CSTR is, let's say, 40 degrees. Now, next thing is, what happens if the temperature of the feed rises? So then the temperature of the CSTR rises from 60 degrees to 70 degrees. Now, systems are multiple types. So suppose systems, the behavior can be like this. The behavior can be like this. What is difference between 1, 2, and 3? What is difference between one? All of them are reaching 70 degrees, but in one is, these are called as sensitive systems. Maybe it takes, let's say, maybe fast systems, or let's say fast acting systems, or sensitive systems. And this third type of systems are called as slow systems. Why do I need to know this one? In sensitive systems, you have to take the control action very fast. Very fast. In slow systems, it is okay to take the control action little slow. Suppose what happens is if my design temperature is 70 degrees, suppose if I don't take the control action in let's say 1 second or 2 seconds, the temperature might cross 70 degrees also. Clear? So this is why dynamics is important. What is dynamics is? What is dynamics is you need to study the system. Control action you cannot design. So basically first point is you cannot design a control if you don't know the dynamics of the systems. So because I need to know whether my systems are fast or slow or something like that, so that then only I can design a control system. Suppose if my systems are slow systems, then I can have a different control strategy. If I have a systems are fast, then I can have a different control strategy. So that is why you need to understand the dynamics of the systems. So that is why the subject is process dynamics and control. First, you understand the dynamics of the systems, then you understand the control. So this is what is dynamics. First thing is before the controller, you have to know what is dynamics. That means if there is a disturbance in my input, then what is the dynamics of the system? This is the first part. Part one of the controller is understand the dynamics. Then second part is once you know the control, then you have to decide should I go for feedback control or feed forward control. What is feedback control is let the disturbance affect me and I will take the control action. So in feed forward, before the disturbance affecting me, I'm taking the control action. So since feedback control is something which we study the entire chapter, a simple feed forward feedback controller is you have a measuring element, you have a controller, and you have a control valve. So this is a simple feedback control. Instead of measuring my temperature of CSTR, if I measure temperature of feed, it becomes a feed forward control. A system which is sensible should also respond to controller. Yes, it has to. Basically, you have to take the control action very fast. See, basically, if you try to understand one question here, PDC comes into picture when you have a changes. PDC comes into picture for dynamic systems. Suppose if the system is working steady state, do you need any PDC? Do you need any control action as long as your temperature of CSTR is 60 degrees? No, no. PDC means you are talking about a dynamic system. So basically that is what clear. Now the subject is two parts: process dynamics and control. How do you study process dynamics? How do you study the process dynamics is right. You have to write unsteady state model. You have to write unsteady state models and solve the models. That is where you will come to know, let's say, dynamics. This dynamics will become input for controller design. So you have to study parameter with respect to times. So that is why you write the unsteady state models. Then you solve the models. Then you write the dynamics. That is where you study the input. How do you solve the models? When you mean by unsteady state models, do you get, let's say, a simple algebraic equations or let's say differential equations? Unsteady state models means you will get the differential equations. So how do you solve this differential equations is using Laplace transforms. That is where somebody might have a doubt why I am studying Laplace transforms here is because you are studying the dynamics. The dynamics solutions are possible using the Laplace transforms. Clear? So Laplace transform. So that is why process dynamics and control, the first point that you study is Laplace transform. What is the link of Laplace transforms to process dynamics and control is you are getting differential equations. The differential equation solving is possible only using the Laplace transforms. So this with this one, so I've let's say the introduction part is done. So we'll start chapter 1. Laplace transforms are useful even for a bigger translations. So that is why if you study process dynamics first and then control later on. First you should study the second is the control action. So we'll start chapter 1. So I'll give, let's say, 5 minutes time. Just take out your notes. Just go through the entire concepts again so that we will have a clarity on the next chapters. Take 5 minutes time. 6:23 now, 6:28. Till that time, just revise whatever we have discussed till now. So basically you have a CSTR, you are trying to, so you have a CSTR and your feed temperature is 40 and you have to maintain at 60 degrees. So it is an exothermic reaction. So you have to remove the heat. So if you remove complete heat, then your outlet is 40. If you don't remove heat, outlet is 100. If you remove 40%, outlet is 60 degrees. That is how we have designed the concept. Morning at what time you are available? Because if I take diary only 1.5 hours, it will take, let's say, more time because I want to complete maybe if possible in 10 days time so that you are available. Morning you already have FM class. Okay. At what time FM class is going on? What is the FM class timings? So 6:45 to 8:40. Okay. I can't take 4 hours every day because I'm also going to office. I can take this time 1.5 hours, but I'm thinking, let's say maybe some extra time in the morning can have an advantage. Okay, let me think over this one. So we'll. So take okay. Maybe I think we'll think about this one maybe later on, but just read the concepts again. So in 3 minutes or 2-3 minutes, I will start chapter 1. So chapter 1 is Laplace transforms. So Laplace transforms and first order systems. So first thing is Laplace transforms. What is the Laplace transform definition? Laplace transform of f of t is integral 0 to infinity e power minus st f of t into dt. So what is Laplace transform of 1? 1 by s. What is Laplace transform of, let's say, t? 1 by s square. What is Laplace transform of t power n? N factorial by s power n plus 1. Okay. What is Laplace transform of sine omega t? Omega by s square plus omega square. What is Laplace transform of cos omega t? S by S square plus omega square. What is Laplace transform of e power minus at? What is Laplace transform of e power minus at? If you have e power minus at multiple, then you have to replace s with s plus a. Because when you put e power minus at into this differential here, what do you get in place of e power minus s? You are getting e power minus s of plus a into t. What is Laplace transform of e power minus at into sine omega t? So I hope you know everybody all this Laplace transform. That is why I'm going little fast. What is Laplace transform here? W by s plus a whole square plus w square. This is how you write the Laplace transforms. What is Laplace transform of df by dt? What is Laplace transform of df by dt? S into f of s minus f of 0. What is Laplace transform of d square f by dt square? How do you write? S square into f of s minus s into f dash of 0 . So what is this one? Minus f dash of 0. Similarly, Laplace transform of dt cube is s cube into f of s minus s square into f of 0 minus s into f dash 0 f double dash 0. So if this is basically first differential, this is directly f of 0. How do you solve differential equations using Laplace transforms? So this is the basically objective. So how to solve differential equations using Laplace transforms is, let's solve this equation. Let's say dy by dt plus y is equal to 1, y of 0 equal to 0. Can you solve this differential equation using Laplace transforms? Solving means you have to write y as a function of time. The objective of Laplace transforms is to solve the differential equations. Why you are getting differential equations? Because you are writing the dynamic model. So what do you do is, suppose you can solve this equation in two ways. One is using Laplace transforms without Laplace transforms. Apply Laplace transform on both sides. Dy by dt plus y is equal to Laplace transform 1. Laplace transform of dy by dt is s into y of s minus y of 0 plus y of s, which is equal to 1 by s. What is y of 0 is 0. S plus 1 into y of s is equal to 1 by s. So what is y of s equal to 1 by s into s plus 1. So if you split into partial fraction, 1 by s plus 1. So what is, apply inverse Laplace transform of y of s. Then what do you get? 1 minus e power minus t. Now we can solve without Laplace transforms. Without Laplace transforms, how do you solve? You have to check now whether this is right or not. Dy by dt plus y is equal to 1. So dy by 1 minus y equal to dt. So apply, integrate on both sides. Then what you get? Minus ln of 1 minus y is equal to t plus c equal to 0. What is y is 1 minus e power minus t. So you are getting the same answer. You have to be extremely good at maths. That is why I told this subject is 95% maths, only 5% concepts. So what is Laplace transform? Next one, integrals. What is Laplace transform of integrals? Let's say integral 0 to t f of t dt. f of s by s. So these are the sum of the Laplace transform that you use in the entire system. So next one is final value theorem. So what is final value theorem is? So suppose if I want to find, let's say, f of infinity, then what this theorem says is limit s tends to 0 s into f of s. What is the final value is? If you have a Laplace transform, you can find out the ultimate value, final value. Suppose let's try with this example. Dy by dt plus y is equal to 1, y of 0 equal to 0. Suppose if I want to calculate, let's say, y infinity. If I want to calculate, let's say, y of infinity, then how do you calculate? So first thing is you apply Laplace transform on both sides. So Laplace transform of dy by dt plus y is equal to Laplace transform of 1. What is Laplace transform of dy by dt? S into y of s minus y of 0 plus y of s, which is equal to 1 by s. So what is y of 0? 0. So y of s equal to s plus 1 into 1 by s. So what is y of s is 1 by s into s plus 1. So now from here, what you should do, you should find out the inverse Laplace transform and put y equal to infinity. But this theorem makes little calculation simple. That is, what is y of infinity is limit s tends to 0 s into 1 by s into s plus 1. S and s will cancel. Final value is 1. Even if you find out y of t, what is y of t? 1 minus e power minus t. What is y of infinity? 1 minus 0, which is 1. So this theorem is giving the right value. Correct or not? So this theorem is helpful for finding out the final values. So can you find out final value for this one? Y of s equal to 1 by s into s minus 1. Can you tell what is y of infinity? Minus 1. So somebody is saying y of infinity is minus 1. Can you inverse Laplace transform? Can you apply inverse Laplace transform and tell me what is the answer? Is theorem is giving right values or not? What is inverse Laplace transform y of s equal to, you should split into partial fractions. 1 by s minus 1, 1 by s. This is inverse Laplace transform. What is y of t? E power t minus 1. So what is y of infinity? E power infinity minus 1, infinity. But actually it is infinity. But then this theorem has given minus 1, no? Why theorem has failed? Why theorem has failed is, can you plot this y as a function of time? Can you plot as a function of time? It is continuously increasing. There is no steady state value, no? So this theorem doesn't predict the values when the system is or let's say unstable. This kind of functions are called as unstable. So this is not a stable system. This is an unstable system because suppose if you're, this is, let's say y is temperature. The temperature is increasing, continuously increasing as a function of time. So it doesn't reach any steady state. That is why this theorem is applicable for all systems if S and F should infinity for any value of, should not be infinity for any value of S. So basically if you see here, what is S into y of S? 1 by S minus 1. That 1 by S minus 1 is infinity for S equal to 1, no? That is why this theorem is not applicable. So this is a theoretical statement, but basically this theorem is not applicable for unstable systems. This theorem is applicable only for stable systems. That is why here you cannot apply. In the denominator, if you have these terms s minus 1, s minus 2, on inverse Laplace transform, they will become e power t. Why this is unstable? Because of e power t, no? Why this e power t is coming? Because of 1 by s minus 1. So this 1 by s minus 1 is what is called as unstable. This is what is called as unstable. This is unstable because the response is continuously increasing as a function of time. So that is why to apply this theorem, s into f of s should not be infinity for any value of s. In the previous case, what is s into f of s? 1 by s plus 1. So this will never be infinity. Why s is always positive? Can s be negative? S cannot be negative because what is s? S is nothing but a domain of time. What is Laplace transform? You are transferring the time domain into a different region. So the time cannot be negative, so s cannot be negative. So this is unstable function. Now another theorem, initial value theorem. F of 0 equal to limit s tends to infinity s into f of s. So suppose if f of s equal to s plus 1 by s into s plus 2. Can you find out what is the initial value? You can do it in two ways. Apply Laplace transform, inverse Laplace transform. Or let's say apply inverse Laplace transform, put t equal to 0. That is one way. Another way is, So how do you apply is limit s tends to infinity s into s plus 1 by s into s plus 2. S and s will cancel. So you can't apply infinity directly, So what we will do is s equal to 1 by a. So what we can do is limit s tends to infinity means a tends to 0. So 1 by a plus 1 divided by 1 by a plus 2. So if you apply this one, limit a tends to 0, 1 plus a by 1 plus 2a. Now you can substitute, which is 1. So you can't directly substitute infinity. So with this one, first part Laplace transforms is over. You have so many problems in PDC from the previous question, so you can solve. So let's take y of s equal to 1 by s into s plus 1. Can you find out what is y of 0? We already know what is inverse Laplace transform. Y of t equal to 1 minus e power minus t. What is y of 0 is 0. You should get. Whether you are getting from this theorem or not, I want to check. So what is y of 0 from this theorem is limit s tends to infinity s into 1 by s into s plus 1. S and s will cancel. S tends to infinity means limit a tends to 0, 1 by 1 by a plus 1. Limit a tends to 0, a by 1 plus a, so which is 0. See here, what is time t equal to 0 stands for is where disturbance starts. Where disturbance starts. T equal to infinity means new steady state. It has achieved a new steady state. So basically what you are talking about here, t equal to t0 stands for the new steady state or disturbance starting. That is where the parameter started to move. What is time t equal to 0 stands for is that is where the disturbance has started. New steady state. I think I will. So with this one, first part is completed. T equal to 0 stands for where disturbance has started. T equal to 0 means that is where the system's dynamics has started. So I have 5 minutes for your doubts. So we'll meet tomorrow, but tomorrow we'll start little early, 5 to 6:30, our regular timings, 5 to 6:30. So what about the morning, let's say 6 to 7, is it okay? 6 to 7, or is it too early for you to wake up? 6 to 7, is it okay if I take the class in the mornings? So I can pull that 6 to 6:45 to 7, no issue. So I will check with the institute and maybe send tomorrow. Definitely will not be there, but day after tomorrow onwards, maybe I can take 1 hour in the morning also. Half an hour we can't do anything. No? Maybe 6 to 7 I will try to take, because I want to. Like, I'm in a hurry to complete, because my opinion is you should start the revisions by December. Now you can't think of, let's say 6 is too early. That is why I told you this 2 months is you have to do lot of hard work. You have to wake up at 5 o'clock, sleeping at 12 o'clock, so 4 hours sleep, all these things you have to do. So don't wake up, let's say after 5, if you wake up, then don't expect a rank below 100. Okay, then okay. Tomorrow we'll discuss. I will discuss with the institute and then let you know. 6 to, let's say, maybe little late, 6:15 to 7:15 or something like that, I'll try. Okay then. So if you have any doubts, I will take your doubts. Laplace transform of y is y of s. Y of s indicates it is a Laplace transform. Y of 0 means at time t equal to 0. Correct. So because disturbance, when the disturbance has started, that is where the systems comes into picture, no? So that is why when the disturbance started is what is time t equal to 0. Like when the disturbance started, that is where your time starts. Suppose if there is no disturbance in the system, then there is no PDC. PDC will start when there is a disturbance. That is where I assign time equal to 0. See, Laplace transform of y is represented as y of s. That is notation. So I will make sure that Fm will not be extended. Maybe I'll push, let's say, little time of Fm. See, the thing is, you have to read daily 10, 12 hours is the only mantra for, let's say, or to study. Wake up at 5 o'clock because morning times are extremely good for the classes or let's say for the reading. Whatever you read in the morning is extremely useful, and that is where I believe you have to wake up now. These 2 months like don't take any chance. This 2 months is not your time. This 2 months is take whatever you should sleep only 4 hours. That is what I can say. Rest of 20 hours you should be reading. This entire 2 3 months so is only reading. So if you do not have any doubts, then we can. If y of 0 equal, that means the disturbance started at 1. If y of s equal y of 0 equal to 1, that means the value of the parameter before the disturbance is 1. That means don't try graphs Laplace. You can't apply like graphs for the Laplace transform. Temperature control of PFR. What you are asking, I am not understanding. You are putting this question 10 times. Temperature control of PFR means what? How to do is using the TIC controllers. You put a temperature controller. Then you have to put elements wise because CSTR there is no PFR, there is no temperature or let's say mixing. You have to put, let's say, multiple elements on the TIC. Or using cooling water at the outlet is also one of the solutions for the PFR also. So you can't say which one is easier or which one is difficult, but everything has its own difference. See, y of 0, 1 means, suppose let's say temperature of the CSTR is 60 degrees. When there is a disturbance, 60 started to move. Now 60 becomes 61, 62, 63. But what is the temperature value at time t equal to 0 is 60. That is what is. Now if T of 0 is 60, that means before the disturbance, the value of the temperature is 60 degrees. See, temperature of the CSTR at time t equal to 0 is 60. That means before the disturbance, what is the value is what is called as initial value. Before the t equal to 0 is also temperature is 60, but your time starts when there is a disturbance. Tomorrow class timing is 5 to 6:30. But you will get a message.